Let's talk about MergeSort. MergeSort uses the divide and conquer algorithm design paradigm. So what that means is, if we have a list that we want to sort, it will split the list into a left part and a right part. And then it will call MergeSort on the left, and which will do some action, and you will get out a sorted left, and it will call MergeSort on the right, so you will get a sorted right. And then it will merge these two lists, so that if you take two sorted lists, how do you put them together? How do you merge them so that all of the elements are in the right order? And this operation is easier to do than to sort the two lists from the start. So just to reiterate, we start with a list, we split it in half into a left and right part, and then we sort the left, we recursively sort the right, and then we take these two sorted lefts and sorted rights and combine them into the original sorted list. Okay, so here's the code implementation. First we print out the list, and then we run our sorted, which will create a copy that's sorted, and then we run inline sort and print that out as well. So we've got those two different implementations. So let's get into what we just talked about through the iPad. We have this algorithm which is going to recursively split the list into a left part and a right part. So it's going to take the middle index, and the left is going to be from 0 to the middle index. The middle index would be here in this case. The right is going to be from the middle index to the end. And then it's going to recursively run MergeSort on the left and on the right. That's what this part is. We are sorting the left, and then we're sorting the right. And then we run this algorithm called merge, which will take two sorted lists and return one sorted list with the elements from those. So this recursion will keep going down all the way until we get to the base case, which is if the array has 1 or 0 elements. So let me actually draw out what it would look like, all of the recursion. So this would recurse, and we would have a left list of 3 and 6 and 5 and 4, 1, 8, 7, 2, and then this guy would recurse into two lists that are each size 1, which would then be combined. This would recurse into these, which would then be combined. So all the work you could see is being done by the merge algorithm. So that's the idea. As for how merge works, we take the output list merged. We have two iterators, one on the left list and one on the right list, and we say while the iterators haven't gotten to the end, so while there's still an element to process, let me just draw this out. Let's say the two lists we have to merge are this one and this one. So I1 would start pointing to here, I2 would be pointing here, and we would say, okay, is I1 or I2 pointing to the smaller element? In this case, I2 is, so we would copy what's at I2 and then move it over. All right, once again, I2 is pointing to the smaller item, so we're going to copy in whatever I2 is pointing to and move it over. Now in this case, I1 is pointing to the smaller element, so we're going to have copy in what I1 is pointing into and increment I1. So that's what this while loop is doing. So in the normal case, where I1 and I2 are not at the end of the list, we just take the smaller one and add that to the list and then increment that. So if the left one, this if statement is if the left one, I1 is pointing to smaller element, just add to the output whatever I1 is pointing to, and then increment I1, which is what we would do here. So in this case, we would add 4, because I1 is pointing to 4, which is smaller than what I2 is pointing to, which is 7. And then we would increment I1. Otherwise, if I2 is pointing to the bigger element, so we can get to that in a... if I2 is pointing to the bigger one, then we're going to have I2 increment by 1, oops, and then put whatever I2 is pointing to here. So that's what this part does. Now, we also have to check if I1's at the end, or if I2's at the end. So let me just do that here. So let's run through one more example. In this case, I1's pointing to the smaller one, so we're going to put this here. I1's once again pointing to the smaller one, so we're going to put this here. And now I1's at the end. So once I1's at the end, then you must process I2, because there's nothing more to process from I1. So that's what we do here. We're going to have this go in, so here, increment, here, increment, and now the while loop's done, because now everything's been processed, so this exits. So we have successfully merged. If this is L and this is R, this is merged, so we can return that. Okay, so just to get the big picture again, for MergeSort, we take the list, we split it into a left part and a right part. We recursively sort the left part and recursively sort the right part. And then we merge those two sorted lists. And merge can take two sorted lists and return out a sorted list with all the items. That's how MergeSort works. Now, there's also an inline version, which uses the indices here. So it's going to start looking from 0 to the end of the list. And then this way you have to do less list copying. We're just copying into the original list our merge value. But the idea is still the same here. So, and then of course, have to have a C++ implementation because it's cool. So this one I used iterators instead of indices as ints. So like we're copying lists here, and then here we're using an iterator on the merged list and an iterator on the beginning and end list. So yeah, otherwise it's the same logic. Okay, and then we can also run the C++ version here. Oh, and by the way, in case you're curious, this function will take in a sorting algorithm and test that it works on a few examples. So this function takes in a function, has these lists, which are a pair of unsorted and then this correct answer, and then it will just run this algorithm and see if the lists are equal. This, by the way, is another function which just checks that two lists are equal by seeing if their size is the same, and then if their size is the same, if all the elements are the same. So it's a good sanity check. And then the last thing is runtime. So if we look at the code, we see that the amount of time it takes, let's say T of n is the amount of time that it takes MergeSort to run on a list of size n. All right, well, we run recursively MergeSort on a list that's half the size. This is the left runtime. And then this line, we run MergeSort on a list of size half, so that's the right. And then in addition, we have to do merge on it. Now, how much time does it take to run merge? Well, the merge runs through all of the elements in the two lists. It has two iterators, and so for each iterator, it's just going through the list. So that's O of n work. So if L1 is size n over 2 and L2 is size n over 2, it's n work, O of n work. So we have O of n work from the merge part. Oh, and by the way, t of 1 or t of 0 equals no work because of our base case here. So basically this t of n is just going to expand this, and the only work that's ever going to be done is by this. So okay, so we're having how many calls are we doing? First we're doing a merge sort call to a list of size n, which then in turn does 2 merge sort calls to lists of size n over 2, which then in turn do 4 merge sort calls to lists of sign n over 4. And we keep doing that until we have 2 to the n calls for merge sort of size O of 1, or 1. And when we do that, this is O of n work from this part. This is O of n over 2 work. This is O of n over 4 work. And this is O of n over 2 to the n work. But that's all multiplied by the number of times we have to do it. So this is times 1, this is times 2, this is times 4, and this is times 2 to the n. So if we multiply those, we end up getting O of n plus O of n plus O of n plus O of n. Okay, well how many O of n's are we going to have? Well, we're going to have log n of them, because how many levels are there? There's log n levels. We only have to split it in half, log 2 of n times. So that means that the total amount of work is O of log n log n. Yeah, so I have a function called plot time complexity, which will take a function, a sorting function, and show you a graph of its time complexity. So on the x-axis we have the number of items in a list, and on the y-axis we have how many milliseconds it takes to run the sorting algorithm on that list. And as you can see, we showed that it was O of n log n. As you can see, that's very close to a line in our complexity graph. And the way this function works is it creates a bunch of lists of increasing size, and then it will, for each list, run the algorithm and see how long it takes, and then it can plot those two things. All right, so that's it for MergeSort.